In this video, we're going to be looking at how can we find the average value of a function over an interval. We do know how to find the average value of a set of finite numbers. If we added up those numbers and divided by the number of numbers that we have, that finds the average value. So for instance, if you had 5 test scores, you would add up those 5 test scores and then divide by 5. That would be your average. But how could we find the average temperature during a day when we have infinitely many readings? So here's a graph that may represent the temperature during the day. We have a continuous function. So we're going to look at how can we compute the average value of this function over an interval. What we're going to do is we're going to divide the interval into n subintervals. So this process is very familiar to us now because this is how we found the area under the curve. What would the length of each subinterval be? We know that would be b minus a all divided by the number of intervals, n. Then we're going to choose the points x sub 1 through x sub n in successive subintervals and calculate the average. Let's see how we could rewrite this expression. We know that delta x equals b minus a over n, so if we solve for n, we would have n equals b minus a all over delta x. Now if we replace n in our formula that we just looked at with b minus a all over delta x and invert and multiply, we would have this expression. Now this is starting to look pretty familiar to us. If we were to take the limit as x approaches infinity, we can see the inside summation would be equivalent to an integral. That's the definition of an integral. So we could rewrite it as 1 divided by b minus a all times the integral of f of x dx from a to b. This will give us the average value of a function over an interval. Here's an example. Find the average value of y equals 1 plus x squared on the interval from -1 to 2. We just saw that our average value can be found by taking 1 divided by b minus a times the integral from a to b of our f of x, which is 1 plus x squared dx. This is how we find the average value on this interval, -1 to 2. Well, this is just a simple integral to solve. We know that to find b and a, that's just our interval. Here's a and here's b. So we'd have 1 all over 2 minus a -1 from -1 to 2 of our 1 plus x squared dx. And then we can take our antiderivative, which we have here. So this is our antiderivative here. And we're going to evaluate that from -1 to 2. And we would 2. There we have the average value, which is 2. Here's the mean value theorem for integrals. This should look very familiar because we just looked at 1 divided by b minus a times the integral from a to b of f of x dx equals our average value, f of c. Well, if we simply just take and multiply both sides by b minus a, we would have our f of x dx equals f of c times our b minus a. And that is our mean value theorem for integrals. If f is a continuous on the interval a to b, then there exists a number c in ab such that, now that c will plugged into our function will give us the average value of the function on that interval. So here is, let's say, that value that we can plug into the function that would find our average value, f of c. What this means is that the area under this rectangle here would be equivalent to the area under the curve. And that's what this is saying. The area under the curve of the function equals the average value times the length of the interval. Well, this is f of c right here. That's the height of the rectangle. And this here is our b minus a. And if we looked at the diagram, the significance of that is this area here, which is area under the curve. This area is not included as area under the curve, but it is area under the rectangle. That area should be the same as this here. So that should compensate for this area that is not under the rectangle. This area here should be the same as this area up here. That's outside the rectangle. So there's our interval from -1 to 2. There's our f of c. That's our average value. And there's the value that gives us, when we plug that into the function, that would give us our average value. And the way I like to think about this also is if you created a bucket and the function here represented some ice that was frozen in this bucket in this way right here, that's ice. If you let the ice thaw, the level of the water after it thawed out would come to right here. This ice right here would melt and it would fill in exactly that area right there. Let's look at how could we find the value c. We can use the mean value theorem for integrals to find this value for c. What we're going to do is we're going to say we know that 1 all over b minus a, and that would be 2 minus a -1, on the interval from -1 to 2 of our function 1 plus x squared dx would give us our average value, this value that we're looking for. Well, we can find the value of this integral right here. We can find that. We can find the value of this integral. We would have 1/3 times x plus x cubed over 3. And we'd be evaluating that from -1 to 2. So we'd have 1/3 2 plus 8 over 3 minus -1 plus -1 cubed over 3. And if we looked at solving that, we would get 2. So this whole piece right here just equals 2. So we have 2 equals f of c. So down here we know f of c is simply 1 plus c squared, just plugging in c to the function. So c squared equals 1. So c equals plus or minus 1. That would give us the average value, and you can see that here. Plugging in -1 to the function also gives us our average value. So that's how we can find the average value to plug in the value of x to plug into the function to find our average value. And this is just going through the diagram of what we just found and showing that those two areas, the one outside the rectangle and the one inside, those should be equivalent areas.